Hello everyone, welcome back to my channel, Black Box Engineering. Feel free if you want to like, comment, subscribe, and if you want to be reminded about my videos, please click the bell down below. Alright, so since I have had a pretty decent outcome with the tech stuff, I'd like to talk about some of the aspects of circuitry that I found confusing when I was in college. Now, okay, so I can understand why college professors kind of leave out details and stuff, especially with those who are really experts in the field. It's hard to simplify things if you know a lot about the thing that you're talking about. And I think a lot of professors don't realize that they're talking to someone who is completely alien to them. So let me give you a couple of examples, and this might actually sound quite familiar to like programming classes too, because this happens I think everywhere. But so an example of knowledge that just kind of like they'll assume that you already know some of the basics or some of the circuits just out of the blue, you know. But the thing is, most most people do not know at all what you mean. It does not help to have something completely foreign to someone. Let me just pull something up here on the web. Something that I still to this day don't really know how it works. Shout out to Circuit Lab here. So I'm just going to share this on the screen here. So this is a buck boost converter. I think it takes low voltage and boosts it to a higher DC voltage. I believe that's how it works. I'm a little unfamiliar with it myself because we never really got taught. So the way that professors would often like approach this thing, they'll just say, "Oh, here's this simple circuit called a buck boost converter. It's pretty obvious what it does." And yeah, this is what it is, and I'm not going to explain anything about it. And then this goes this way, and this goes that way, and yeah, you just got to make sure to activate this through this, and but they don't tell you where this comes from. Like, no one ever explains where the freaking clock signal even comes from. I learned that you can literally just generate this through, like, I don't know, like a 555 timer, or even just like an Arduino. Can get a frequency, a square wave frequency, into the gate of the MOSFET here. That's literally all this means. But it was never explained in class. Like, oh, it's just ignore this for now. We'll get back to it later. Newsflash, we never got back to it later. So stuff like that. And there's just these random like examples where we would cover a quite complicated concept and we would never expand upon it. So another thing that I found annoying, and I had no clue what my teacher was talking about, the fact that, so let me just like draw something up real quick so that I can explain this. So let's say that we had a simple, in this case this would be a pretty simple circuit. I'm not actually gonna do what those teachers do here. I'm just gonna have a simple resistor network here. So all this, let me just give these values here. So technically this is a 10 ohm resistor in parallel with a 50 ohm resistor, because these are in series, so they just add up. I just didn't simplify it, so whatever. There would be, how did they phrase it? They would always say, without explaining what they meant at all, they would say, well, you know, ground is a reference point to the circuit. And I'm pretty sure, like, approximately 80% of the class was like, and me too, because I had no clue what they were saying. A reference point to what? Well, you know, a reference point. Yes. Okay. A reference to what? You know, a reference point for the circuit. Technically, it's true, but it doesn't help when you don't explain what you mean. The best way that I think about it is a reference point to 0 volts, because in like actual circuit analysis, everything has to add up to 0 when you do like a complete circuit. So like if you were to follow the line, let's say your starting point was here, you would hit a negative 20 volt value, since negative is first. You would do your I times R, so we don't know what the current is, so we just do, I don't know, like X times 10, so you'd have negative 20 plus X times 10 equals 0. That would be a valid equation for this particular, this mesh is what they call it. This loop right here is that's a valid equation. And because we go back to 0 when it comes to loops, to me it makes the most amount of sense that this is the 0 volt reference point. And technically, if I were to run this, it doesn't let me do anything, but if I were to measure from positive to negative, we would get a plus 20 volt, because we're going from 20 to 0. If I were to go the other way, from 0 to negative to the other way, we'd see a negative 20. So yeah, so the current would be 2 amps, because 25 by 10 is 2. And then let's see, so the other current would be, let's see, 50. 20 divided by 50, that's going to be a pretty low current. That's going to be like less than 1. Yeah, 400 milliamps. And we would have to say that 400 milliamps plus 2 amps is going to be 2.4 amps total, which is what we see on the current on the line that has no resistance on it, because of the KCL law. But anyway, it always bugged me that no one explained that, yes, ground is a reference point. You're measuring in reference to ground, but you can't just say it's a reference point and not get questions of, well, what is it a reference point to? Because that's the most logical thing that follows from that. In my mind, it's a lot easier to say, well, it's in respect to 0 volts. And it just seems to make a lot more sense to be that, because let's say if I were to make like a voltage divider, for example. So let's just delete some stuff here. Let's make this 20. So, if I run this, we should be getting a total of 20 over 30, which is 0.666 milliamps. So, you know, it'd probably just make more sense to make it 10 to make it 1 amp. Yeah, so let's say that this is what we want. So this would split the voltage in half. So from positive to negative, we would see 10 volt on from 10. This node to this node is 10. But if you were to measure between here and here, I think it would also be technically 10. Yes, because it's the same voltage difference between here and here and here and here, because we're literally splitting in half. If I were to decrease this to 5, we're going to get 13.33 volts from here to ground, and then from here to here it's going to be a lower voltage because more current, so less voltage. So 6.66 volts, or yeah, 6.6 2/3 or whatever. Yeah, so to me, if it makes a lot more sense to say 0 volts is the reference point that we're measuring in respect to. But here's another thing that kind of bugged me when it came to circuits, and this is something that was never explained in class. They just kind of drew it this way. So they would have something like this, and then they would have a bunch of resistors and maybe some capacitors and stuff like this. And if I click the right things, so yeah, something like this. I'm probably exaggerating, but it's just to make a point here. There would be a lot of things where you would have these floating like things on their diagrams on the chalkboard or whiteboard or whatever they were drawing on, and I had no clue what was going on, because this doesn't make a whole lot of sense. This is something that you just kind of pick up in the industry. This is just short form for making parallel circuits. So the reason that engineers and other companies do this kind of thing, so when you're talking about ground, it is rather difficult to, realistically speaking, it's rather difficult to literally bring everything back to the same ground like point on a drawing. Like, imagine if we had like 50 resistors and other components parallel and series and a mixture, and this became like a huge circuit. Imagine trying to connect all these different ground points to one singular point. That'd be really hard to do and pretty much impossible when it comes to more advanced designs. So let me just let me see if I can find a good example online, because I'm not making much sense. I'm not going to draw something out. Complex circuit diagram. So, as you can see on Stack Exchange here, this is a processor diagram. A very complex circuit becomes pretty much impossible to draw everything to one singular point. You just run out of space, and you see how there's a lot of different floating components. So what I learned is, and this was through trial and error, is that these ground nodes are literally all interconnected through one plane, maybe multiple planes depending on how a printed circuit board is designed. But anyway, grounds are typically tied together. So ground is literally like this whole one point of return that a circuit has. Sometimes there might be different ground planes for different things. That's overcomplicating it for now. Let's just say, for the lack of a better term, in most cases for less complex analog circuits, you've got one ground plane that where everything returns to as the 0 volt reference point. In reality, they're a lot more complicated than that. But anyway, because sometimes you don't want the certain ground planes to mix together. It's just important to know that depending on the signal type and whatnot, you may not want to have the same ground reference for signal versus power. That's a big no-no sometimes. So anyway, so having shorthand form of floating components and various like little ports that you can't really make it out too well on the screen here, but you see these like floating ports. These literally just mean like external signals from somewhere down the line, probably like a different related circuitry for this. But yeah, all these actual like points are going somewhere else in a completely different diagram. It's just not drawn because you run out of room. Again, I wasn't aware of this. Like, I thought that these things just went nowhere. Uh, I like this joke one. Yeah, I just thought that things just terminated nowhere, and that like where does it go? And boy, they never explained any of it. And so if I just come back to the simulation here, this is literally the same thing. If I got rid of these floating ground points to this, to that, that's all that means. And boy, did it ever annoy the hell out of me. I wish they explained like the shortcuts that they talk about, rather than just say, "Oh, this is this is this, blah 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 blah," and they fly through it and confuse people further. So yeah, any floating like ground point in, and I'm not talking about like floating ground is a completely different. There's a real term in actual like engineering called a floating ground point, where it's not like, let's say if you have an isolated circuit board and it wasn't tied to earth ground, that'd be called a floating ground point. But that's not what I'm talking about. I mean, in a circuit diagram, a floating ground point, or like a detached ground point, may be a better term, not to confuse it with the other one. So a detached ground point or a detached component is always going to go somewhere. It just might not be in that particular diagram, or in this case, let's like a ground reference all those grounds are technically tied together. The software knows that, and the expert knows that, but a new student doesn't. And yeah, so the same thing happens for like I was telling you, like voltage reference nodes. So another way to save space on a complex circuit is to have these things called voltage nodes. Let's say you wanted, like, I don't know, a 60 volt reference point and we wanted it to be an output. I could literally leave this alone now, and this 60 volt flag will literally be the same 60 volt reference point wherever I choose to have it. Of course, I want to make these out. I'll just leave it output. I don't need to change. Okay, I'll make this an input, and these ones. So no, sorry, backwards. This an output, these inputs. Let's hide the graph here for a second. I'm just going to shorten things up here. Alright, so yeah, like something like this. This isn't matching. Let's make it 60 volts just to keep it consistent here. So I could literally have this way over here, and the transient thing too, and then I can run this, and then every single one of these will be the same 60 volts everywhere. And this saves a lot of room in actual schematics, and especially with like teaching like stuff over simulation stuff like this. So this is like a total of 1.054 60 volts, drops down to 54.8. That shows up as negative because of the way that I'm probing it, but it's just telling me how much the whole thing actually draws. If I were to add these up, it should be the same number but positive. So this and this and this. This should add up to 0.692, 1, and 1.05. .03 plus 0.692, 2.745, 2.74. Of course, I didn't include all the decimal points, but like I said, it's going to be the same answer. Close enough. That works. So yeah, it's just a quick way of like doing a lot of different circuits and organizing things quicker, but it's never explained. And yeah, these are the things that I always found annoying in circuits class. And then because of the lack of time, especially with my classes, mine were much shorter. I think like 6-week condensed classes or something like that. We got even less detail with like complex circuitry. We were never really fully explained like how buck boost even works. we never we never were taught like anything about negative voltage stuff. We never were able to like really connect theory to actual practical application. And that's something that lacks in most colleges, I'd have to say, because everyone online seems to say the same thing, where there's a lack of actual practical stuff. And the thing is, at a certain point in electrical engineering, theory becomes really important, but not. It depends on what you do, I guess. If you're like a super genius and you're designing huge computer systems and stuff like that, well then yeah, theory is gonna be a huge thing to know. But when it comes to like working at a job where you're not developing ultra complex things, it is a typically it's a granular approach where like I've described, they give you like more simple parameters, and you're asked to design around those, and it doesn't even necessarily have to be complex. You just gotta know like basic circuits, basic concepts. Maybe you could get into like some analysis, but usually like tools like workbench tools or whatever can do that kind of analysis for you these days in companies. And there's just not much of a need to actually do the handwork when it comes to real engineering. I'm not saying it doesn't have value, it just things have moved on from using our hands in a physical writing sense, and people focus more on, well, we've already got solutions in place, we just gotta expound upon that by reading a bunch of data sheets and getting a system to work without really having to get into complex theory. Again, depends on what you do, but I just wish that there was a better way of teaching that kind of thing. I wish there was like a shortcuts kind of thing. I had a really good book. I can't remember the title of it. I'd have to bring it out sometime. Like practical applications of electrical engineering, something like that. Instead of going over the complex theory stuff, it covers the things you should know, the basics. It tells you like these different compartments of knowledge. Like it gives you the organization of a circuit, and it doesn't necessarily explain it in a highly technical fashion, but rather it breaks it down into like how the mechanism works itself. Because technically, all that buck boost is really doing is it takes advantage of pulse width modulation. Higher frequency pulse on the MOSFET makes the inductor in that whole circuit increase the voltage, because of how inductors work, and then the diode just limits the current from going absolutely crazy, because clearly you don't want a huge current spike in your application, so that protects against that. So anyway, I'm kind of talking around in circles and rambling on. So I hope that you kind of gain some knowledge on like shortcuts that you might see in a classroom, and I hope some of these explanations have helped. It took me a lot of troubleshooting on figuring out how these simple, in other people's minds, simple circuits work by trying to decipher. I think working at a tech company as an electrical technician, by like reading a bunch of data sheets helped a lot, because there would be like circuit diagrams and I'd have to try to interpret that, and then I made connections like, oh, this symbol keeps meaning ground, and I think I did like a Google search and I said, is ground connected? And then that said yes. I'm like, wait. Oh, so all these disconnected things are all interconnected. And then it was like, kind of thing. So anyway, yeah. Just let me know if you have any comments. What other things bugged you in any kind of class? It'd be programming or circuits or whatever. What thing really bugged you when it came to vague teaching? So it's always fun. I'm glad that college exists, but man, teachers need to be better at explaining the simple things and the like shortcuts that they use, and they need to give details on things that don't have any context to. So, see ya.